We present SPH fluid tactile rendering for ultrasonic media haptics, where our method estimates the target pressure field by filtering local maxima and compute a set of focal point for amplitude modulation. In our daily life, we experience the presence of fluid on the skin surface by the changing pressure distribution. In virtual reality, the tactile rendering method can produce the pressure field by the rigid fluid interaction. To generate the pressure field, we use the ultrasonic media haptic interface, which can generate the acoustic radiation force to the user's skin. In our method, we extract a point cloud which represents the surface of virtual hand. Each rigid particle is computed by using the depth and normal textures of the virtual camera. We use point cloud for SPH simulation and tactile rendering. We compute the rigid fluid interaction using weakly compressible SPH simulation with versatile approach. Moreover, each rigid particle has wall space normal so that we formulate the pressure field using the applied force by the fluid particles. Our tactile rendering method generates a set of focal points to estimate the simulated pressure field. The estimation procedure is into 3 steps. First, we compute local maxima from the target pressure field using parallel computation. For each corner, we use an iterative gradient ascent to find its local maximum. Second, we sort local maxima into descending order based on its pressure value. Finally, we select n focal points which can modulate in the ultrasonic media haptic device. We use fourth distance filtering from the sorted local maxima. The selection procedure is performed as left-hand side figure. If the selected local maxima is only accepted when it is further than separation distance. From our rendering method, the root mean square error is shown as on the right-hand side table. We compute the focal point information from the position and pressure in virtual environment by the filtering results. The location, intensity, and modulation frequency are formulated according to the simulation parameters. Our simulation and haptic rendering run between 90 and 100 Hz, which is considered as smooth and stable rendering rate in the fluid haptic simulation. We performed a user study to examine our fluid haptic rendering that improves the simulation realism with respect to hand posture and motion. A pair t-test and post-hoc test showed that there was a significant difference in all questions. This is a demo using our fluid tactile rendering. The user can manipulate the virtual shower by using motion controller, and they can experience the various fluid properties. In this presentation, we present SPH fluid tactile rendering and its application. Thank you for listening.